The following program is brought to you by Caltech.
Well, good evening, everybody, and good evening for the associates who are in Northern California actually watching this event at the same time as you are doing this. I'm Charles Elashi, Director of JPL, and I have the pleasure today to introduce our speaker. But I need to make two first announcements. Number one, we will have an informal question and answer session. So at the end of the talk, people can come to the front here and talk with John. Because John is planning to take the full hour because he has so many exciting things, to tell us about. And the other thing is to tell you that the next meeting is, or the next talk is on May 22nd by Professor Shu Shan, and it's on decision-making and quality control in early moment of a protein life. So now coming back to tonight, I want to take you back to the evening of August 5th, around 10:30 in the evening. I will bet maybe the majority of you, if not all of you, were either here in the mall, at Caltech or at JPL or watching your TV or watching the internet, joining in one of the most exciting things that have occurred, in the United States over many, many years. It was a very dramatic event, both technological, where a car-sized rover was landed on Mars, but equally, it was a human drama where you saw the excitement and the tension that the people who have worked on this project were sitting down watching what was actually happening. And there was at that night, there were 50 million Americans, who were watching, that event anywhere around the country, Times Square, at their home. And the following day, there was 1.6 billion hits. That's billion with a B, billion hit on the JPL website. Of people, wanting to see what's happening. Now, some of it was myself, checking every 5 minutes, what's going on. But still, it was a very large number, which was doing that. So after those 7 minutes of terror and few weeks of checking out, then the key was passed from the engineer to the scientist, the team of scientists, which led by John Gratzinger, who's going to be our speaker tonight. So he's going to be telling us about what kind of fun they have been having and what discovery the science team have been doing over the last 8 months. So let me say a few words about John and not take much of his time. He graduated from Virginia Tech. Then after a number of activities that he had done, in Oman and in any place around the world, he was at MIT. Then one day he woke up and he said, "Why in the heck am I at MIT? I'd better go to that great other school, which is called Caltech." So in 2005, we had the pleasure of having him join Caltech. And John is, in one word, one of the worst leaders in sedimentary geology. What that means in plain English, that he can take a rock and tell you the history of the universe by just looking at that rock. And basically what he and his team have been doing is doing that same thing on another planet through the eyes and the tools of curiosity. So please join me in welcoming John Gratzinger.
Okay, well, thanks a lot for inviting me to do this. And I want to start off by acknowledging all my colleagues that work on the mission. I'm the spokesperson for the mission. There are 458 team members, science team members right now, and they represent about a dozen different countries and over 30 different institutions. So, we at JPL are managing this mission, but the science team members are really the engine for all of the work that gets done with our colleagues in engineering at JPL, which I'll say something about at the end of this. The other thing is that there are 9 principal investigators who have built the science instruments, and I'll go through that a little bit as we go along here. So it's just important to recognize that this is really a major enterprise and kind of a team experience that we all share together. Before I go on, let me just, you can ponder this a little bit as I talk a little about the history of rovers. This is our field site, Gale Crater. This is Gale Crater. And in the middle of it is a major topographic feature we call Mount Sharp. And if you look at that, what you should immediately notice is that all the rest of these craters, there's no mountain in the middle of them. And that's why we picked this site. There's a whole bunch of other reasons as well, but it's a really interesting feature. As we skip on, you have this nice view of the planet, artist's conception. Okay, so let's go back and talk a little bit what we're doing on this mission. And the scientific objective of Mars Science Laboratory and the Curiosity rover was to explore and try to discover a habitable environment. And I'll go into that in a little bit. What we mean is that we don't just have a source for water, we now also have extra observations that are required to define an environment that would have been inhabitable by microorganisms if they had ever originated and evolved, okay? And the if and the rest of it is not what I'm going to be talking about tonight. We're just looking to do environmental chemistry in rocks that are billions of years old, try to reconstruct what the planet was doing. The way that we got there was via the Pathfinder rover, which landed on the 4th of July, 1997. And NASA had set up something called the Mars program, which gives us a context to do repeat missions to Mars because it's so close. We can, if we get our act together, we can do one of these every 2 years if the budget allows. So the idea was to go back to Mars, and this time instead of a lander, have a rover. So Pathfinder was what we call a technology demonstration, a tech demo. It wasn't really supposed to do any kind of significant science, although it actually did sort of rattle around and make measurements of the geochemistry of rocks, and it took some pictures and stuff like that. But it was very successful, especially in the engineering context, that this is where we had this bouncy airbag landing system that hadn't been tried before. And it seemed just as improbable back in 1996 that thing would actually work. So that allowed us to then move forward and follow through in the next decade. And so then we got Spirit and Opportunity here that both landed successfully back in January 2004. And now we go from something about the size of a microwave oven to something the size of a golf cart with the rover. And this time around, you have the same rocker bogie suspension that you had down here in the tech demo, but you just scale everything up and now you add some substantial science. And the goal of this mission now was very scientific. It was send these rovers to 2 different places and see if you can find evidence on the ground for the water that you think you see from orbit, right? So we have orbiters going around the planet, mapping them and looking for evidence by taking pictures and looking at spectroscopic information about whether or not there's water involved in these ancient rocks. So there were 2 keys. The one was to go ancient, because Viking was such a bummer from the point of view of looking for evidence of life on the planet today. Maybe it evolved, but it just became extinct or something, or went into the subsurface where we can't see it. Let's go back and interrogate the ancient rock record. And we need to do this with a rover, because geologists on Earth, you don't just get out of the helicopter or Jeep and make history based on looking at the rocks that you land on. You have to go around and make sort of a geological map. So that was the goal then of this mobile platform. And then anticipated already even before the time of landing was that if that mission was successful, then you go to the next level and you build a mobile geochemistry laboratory that you can send to the surface and drive around and look to explore the next level of habitable environments. And then if this is successful, and I think we feel comfortable with that now, then you go to the next level and you get another rover that maybe begins the path to returning samples back to Earth. So this has been a very successful program, and we're still on that trail. Okay, so let's take a look now at Curiosity, and probably many are familiar with what it can do, so I'll just hit some of the highlights here. We basically break the instruments into 3 groups, and the first group is what we call remote sensing. So we have a mast that sticks up above the top of the rover. We've got cameras up there, mast cam they're called, and these cameras basically take color images, HD resolution, and also video at 5 frames per second. And then in addition to that, what we've got is a laser, and that laser can reach out about 7 meters, that's about 10 feet or so, right out down there on the ground. And what we can do is we can basically burn a rock. So the laser packs enough power, it's about 10 megawatts per millimeter squared, and it creates a plasma, and then we look at the light that is emitted from that plasma, and we gather it in a telescope, send it down a fiber optic cable into the belly of the rover, into some spectrometers, and that tells us then about what, in a crude way, what the chemistry of this rock is. And so if we decide we really like that rock, then we drive up to it, and now we go into the second group of instruments, which we call contact science, because we reach this arm out and then put these instruments on here onto the rock. Now this arm is like our arm. It has 5 degrees of freedom. So it goes up and down, it goes this way, then you've got a elbow joint, and then you have a wrist that can turn around. And so basically, although the instruments out in front here, this turret, as we call it, is about the diameter of a trash can lid. We can't get into nooks and crannies, but we can get to the things we really want to anyway. And then if we decide that we really like it, because this instrument gives us a much more quantitative impression of chemistry measurement, and then we have MOLLE, which is a hand lens, again, color, HD resolution, makes movies. If we decide it looks really good, then we drill. Or we scoop it if it looks like a soil. Then we take the drill, the arm reaches around after it's done drilling, reaches over the top of the rover, these flapping lids open up, and then we drop the sample, goes down into the rover, and then it goes into these 2 instruments here that I'll talk about in more detail later. But they are what makes this a mobile laboratory. SAM is a complex of 3 different instruments, and I'll describe a little bit more about it later. And ChemMin is a X-ray diffraction unit. And so this gives us a lot of the capabilities that we have here on Earth. Okay, so now let's look under the hood here at the most complicated spacecraft, most complex spacecraft, most capable spacecraft that's ever been put in outer space. And what we see is the SAM instrument. And a minute ago, I mentioned this one. The SAM instrument basically has 3 sub-instruments in it. It's a quadrupole mass spectrometer, tunable laser spectrometer, and a gas chromatograph. And you basically take sort of 2 or 3 rooms of equipment that we would have here in Caltech, and then you put it down and shrink it all and put it into a box the size of a microwave oven, and it only costs you $90 million. This is our X-ray diffraction unit over here, and again, we miniaturized that down to something about the size of a toaster. Here's some other interesting features. Spacecraft computers. This rover's so big and so expensive, we couldn't do 2 of them. NASA wanted to do 2 rovers back in 2004 to mitigate the risk that one might fail. And this time around, we didn't get to do that, but what we do is we still have redundant computing. So we have an A-side computer and a B-side computer, and some of you will know that about a month and a half ago, we had an anomaly, and what we wound up doing was basically booting from the A-side over to the B-side. And on the A side, we suffered a little bit of damage on our flash memory, but we know where that is, and we can basically map around it and still use that if we want to. So we have that redundancy, and in this case, it was extremely important that we did have that. Rover motor controllers, we've got 39 motors that actuate different sorts of processes that the rover can do with its hardware. Electronics to sort of bus everything around. Lithium-ion batteries that we use because sometimes using these instruments is so power intensive that our power source, which is a plutonium-238 thermoelectric generator, it sits back here, and that power source generates about 100 watts of power. That's just not enough to get the job done, so we have to draw off the grid, and we've got these batteries over here. And then we've got radios that allow us to communicate to the satellites that pass over the rover several times a day. And then the X-band radio allows us to communicate directly to Earth, and I'll talk a little bit more about that later. Okay, so here's our field site. I mentioned in that first picture this strange-looking crater. You look all over the place here. This is the only one that's got a mountain in the middle. And the odd thing about this mountain is that the elevation, the summit of that mountain, is the same elevation as the south part of the crater rim. So it's way above in elevation the northern part of the crater rim, and it's way above where you would ever predict to be sort of what's called the central uplift that happens when you smack a big impactor down on the surface of a terrestrial planet and you get bounce back. That bounce back never achieves the height of the crater rim. So this was a big mystery. It's very interesting to us because of what we also saw additionally was the evidence of water. Here's part of it. If you look around, you can see these channelized networks that are running across here. And the scale, basically, you're going from higher elevations here to lower elevations in this direction. So basically, there's a slope that's cutting across this, what's called the dichotomy boundary on Mars, that separates older southern highlands from younger northern lowlands. And apparently water was part of this story, just flowing across here. So when we looked at this, and there was all kinds of action involved in picking the final landing site, because the engineers got us into every one that the scientists wanted to go to. And in the end, we had a final four, but we had to pick one. And in the past, the engineers always took them out, and we were sort of left with whatever we wanted because the spacecraft couldn't get in there. But with this EDL system working so well, it was left to the scientists to kill each other to figure out which one they wanted to go to the most, and this is the one that won. And after all the complicated arguments, the one that made the biggest impression on me was the simplest one of all, which is that after all the smart evaluation is done, you still know that water flows downhill, and the path of this network is right through the middle of this bowl. And so you have a closed topographic contour here. There was a chance that you might have gathered some water. Okay, so here's now one of my favorite reconstructions of Gale Crater, because it's based on many different generations of data. And the color that you see here is the last time NASA flew an orbiter that could take colored pictures. It was Viking back in the 70s. You see color pictures in more recent missions, but those are all false color images. So what we've done is to wire wrap that color on top of the topography. Here's the summit of Mount Sharp. Here's where we landed. This is our landing ellipse, which is the long axis is 20 kilometers in scale. Where we wanted to land, targeted to land, was right in the center of the ellipse. And you can see that we basically came in this direction. So we went down track just a tad. And that's like teeing off from Tokyo. And you want to hit a window in the Empire State Building, and you miss by one window. So these guys are really good at this, and what we wanted to do was get this ellipse as close as possible to the base of the mound here, so that we could study the rocks that were right down here at the bottom. But the elevation difference between the summit and the ellipse has more relief than Mount Whitney does above sea level. So it's over 3 miles high in elevation, about over 5 kilometers. We don't intend to drive up to the top. We just want to do the lower stuff. But who knows what will happen. Okay, now we zoom in a little bit more. Here's our same landing ellipse. And now I've sort of turned it around on you. So now north is up in this direction. And what you can see here are these channels that are running out of the crater rim. And they're depositing a feature that many people will know as an alluvial fan. You drive out in the Mojave Desert, you look at the mountains, you see these wedge-shaped features coming towards your car, and those are ancient river deposits of sand and gravel. The interesting thing about it is that out in front of what was obviously an alluvial fan, and so we had a very strong indication that there was water here at one point transporting the material that made the fan, was this red colored material down here. Now, what we've mapped here is a property called thermal inertia. And so this is the ability of rock and soil to basically retain its heat late into the day. So if you've ever been walking down a street and the air is cool in the evening, and you walk past a building and you feel that radiating warmth, that's what's getting mapped here, okay? So the orbiter is passing over Mars while it's dark, the sun is down, and what it's picking up is a lot of heat coming up from these areas that are red. And it's interesting that this basically sits right out in front of this fan, and that was an additional magnet for us. We don't really know what it means. Thermal inertia is a complex property. We still don't know exactly what it means. But we decided that when we realized that we landed here, that it was so close to some of this stuff that rather than drive towards the mountain, which was our original goal, we decided to drive in the opposite direction and check this out, just because it seemed like it was going to be interesting. Okay, so now back to the lab. Here's Curiosity, just about ready to go and be shipped to Cape Canaveral. And a lot of people ask me, what went right with this mission? And there's so many things to point to, but one of the most is what I learned as a scientist hanging out with these guys at JPL is that there's a mantra. It's like for real estate, you've all heard it, location, location, location. In this case, it's fly as you test and test as you fly. And you don't ever build anything that you can't test. And then when you've built it and sent it, you don't operate and do anything without testing it first. So what's happening here is that this engineer with this white suit on is trying to not create thermal interference as we shine a light down on the rover that has the intensity of the sun on the surface of Mars. And the engineer is going to hold this probe out, and at the end of it, there's a little temperature sensor, and touch the various parts of the rover to sort of measure its skin temperature. And that's important because every day on Mars, we have a temperature swing of about 100 degrees centigrade. And this rover is built out of a lot of aluminum and titanium, and those metals are expanding and contracting. And when the arm is out, the rover is almost 4 meters long end to end, and you got a drill in the ground that's a 1.5 centimeter hole, and you decide you're not done with the hole or something happens, and now the rover is tugging on this thing. That's not good if you don't really understand the behavior. So these thermal environmental tests are extremely important. So I decided to pick this one out just to make the point that testing is incredibly important. It's why it takes us so long to do most things on this mission, because we got a lot of different systems to operate. Okay, so then the time came to pack Curiosity up from the high bay. It took about 6 years to build, pack it up into a container that's purged with nitrogen, and then put it onto this tractor trailer, and off it goes to March Air Force Base out in Riverside, put on this C-17 along with that crazy sky crane device, and then they fly it to Cape Canaveral, and then basically take the rover and integrate it into the aeroshell, which is one half of the clamshell that makes the spacecraft that enters the atmosphere. And here you can see the cruise stage up here. This is what keeps everything alive on the trip from Earth to Mars. And so these engineers are basically bolting Curiosity on to the aeroshell. Then the last thing to come along here is notice these springs right here. They're important because they are what force the heat shield off. The last thing is to basically clamp the heat shield on, and these springs, when the time comes to eject it, you're going to basically blast some bolts, and then that heat shield will hopefully detach and go off. But this is the last time that any human being saw Curiosity. And then the night before the launch, I had the happy opportunity to work my way on KFC and just basically follow the lights around until I got in there and took this picture with my iPhone. It's kind of amazing, actually. I was driving around, I kept thinking they were going to come in with guys with black suits and throw me out, but it's amazing. All you need is a JPL badge and you can do anything. So Curiosity's up here, right behind the flag, and this is an Atlas 541 rocket, which is sort of the standard configuration launch vehicle for launching heavier satellites into low Earth orbit or many planetary missions. Then we launched the next day, and that was the day after Thanksgiving, so everybody else was out on Black Friday, and we were launching rockets, and it was really cool. It was just a perfect day, and the launch went very well. And then basically you have this long phase through cruise, which took about 8 months. About 10 days after the launch, we turned on our first science instrument, which is a radiation detector that measures background solar and cosmic radiation, and that was provided by the branch of NASA that does human advanced studies for humans on Mars, and you need to know what the radiation dose is that an astronaut would experience on its way to Mars. So we were already doing science before we landed. So what I'm going to do now is, Charles mentioned the 7 minutes of terror. This really is kind of a landmark video. Even if you're not interested in science and technology, it's interesting from a cinematic point of view because the guy that made this, John Beck, kind of went out of the box. And what he did was to film all the lead engineers that were responsible for the different subsystems, and you can see kind of the way he uses lighting. There's a little film noir effect going on. But this really exposes the soft underbelly of this, and it's kind of unprecedented and basically showing all the risk as apparently as possible before we landed. And so it was very progressive from that point of view. So I'll just let that run. If you've never seen her on a big screen, it's really good.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we are facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the Skycram maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Okay, so we made it. You guys know the story. They don't want to think about what would have happened if we didn't make it, but the science team, you looked at this image and you realized right away that you had a mission. And you know, what was fascinating is that basically the rover was programmed to take a picture through the hazard avoidance cameras 10 seconds after we landed. So here, this is that one with the dust cover on. Of course, the dust covers are, you can see through them, because if they never actually opened up, you'd still want to be able to get some pictures somehow. So you can see the dust here, and what you can also see is maybe an outline of what might be Mount Sharp. And then 39 minutes later, we take another picture, and now the dust cover is off, and you can clearly see Mount Sharp over there with the summit clearly revealed, and we knew that we had a science mission. You can also see the length of the shadow increasing due to the difference in time between when we took the pictures. So that was the data we got. And then we went home, and you know, Charles was checking his email and the website, and we were really, actually, we had to go to work, because basically, you know, that's when the science team works, is when it's nighttime on Mars. There wasn't much for us to do, but the next day, we began to get more data. And we discovered that the world was watching us. And I realized right away, many of us did, that this mission was not going to be like MER. There was a lot of public attention aimed at this mission, and that has sort of set the tempo for how you do science on this mission. It's a very public type of process that I hadn't done much before, mapping in the sort of the swamps of Siberia by yourself. But that's the way it is, and it's great to have that, because these are the people that are paying for it. Here's one of my favorite images, which is we then stand the mast up, take a 360-degree view, and what you can see is you can see the crater rim. And we had been really fixated on Mount Sharp because it's such a prominent feature, but the crater rim is also kind of cool. And in the foreground, you can see basically where the thrusters, as the sky crane was lowering the rover down to the ground, there was still enough velocity, there was enough impingement here that it actually blasted the soil away. And some of that soil wound up on top of the rover. And we actually felt reasonably lucky that there was no significant damage. We did damage one of the 3 wind sensors on the weather station, but we can work around that pretty well. That hasn't caused much trouble. So then the next day came, and we got data that involved now pictures from the color cameras, and here you can see the crater rim, these channels that you could see from orbit that looked like they were conduits once for water, probably billions of years ago. And then in front of it, you see this rock that has this layering in it. And it's rock. It's not soil. It's not this stuff that we see here. This is actual rock. That's the stuff that from orbit had the red color on the map. That's this high thermal inertia stuff. But here, it's quite a long drive away. We found our place was over here somewhere, where it was just 500 meters away. So, you know, this already, the people that were sort of doing mapping were beginning to put the pieces together. Then we turned and imaged the other direction, and initially you see this view of what looks like every other Martian landscape that we've landed on, with a bunch of loose dark gray rocks laying around, a little bit of windblown sand. But the difference is this time is when you get all the data back, you begin to see the foothills of Mount Sharp, and you realize, you know, this is a view that we as humans have never really seen before on the surface of Mars, and it looks very Earth-like, especially when you blow up the picture. And you see these buttes and mesas that now remind you less of the Mojave Desert, and they look more like the Four Corners area. But this is eventually where we want to go. And the layers that you see here are basically recording these early environments of Mars, billions of years ago. And our goal is to sort of read it like a book. Start at the bottom, those are the first chapters, then go through this layer and this layer. And when you go through the different layers, it's like turning the pages in a book. So we don't know what the story is going to be, but we're pretty sure it involves water, and we hope to get there. Maybe if we're real lucky, we might be there a year from now. In the meantime, we were checking out the spacecraft, and time came down to start using the laser for the first time. So we looked around. That laser only goes out 7 meters, so there was no bedrock near us, and we just had these loose rocks. And so we took the biggest rock that we could see. It's about the size of a hockey puck, and the science team basically decided that was their target. They wanted to take a shot at it. So here's what the data looks like that comes back when you do something like that. This is this emission spectrum. And so we've got 3 spectrometers, and there are different colors here, but basically you go from the UV all the way to the near infrared here. And everywhere you see one of these lines that sticks up, it's telling you about the elemental composition of this rock, at least in sort of a qualitative way. It gives you a rough sense of what's it made out of. This worked well enough to convince us that this rock was made out of something called basalt, which is a very familiar rock that we see on Mars as well as Earth. Now, what was kind of interesting, you know, it's a little bit like rubbernecking. The science team wants to know, well, what kind of damage did we do here? So we take pictures both before and after, and this is about as bad as it gets. And we've now done this thousands of times, and every time we always take a picture because you want to know what you analyzed. And so seeing where the spots are is basically how we map back to what part of the rock we actually zapped. But that's about as good as it gets. Now, here's what all these people out there that are watching think we're doing. You know, so we know now they're having fun, and there were lots of these, and we were entertaining ourselves, and these were my kids' favorite. Seemed inevitable. Somebody had to do that. And a lot of people ask me, you know, how do you guys drive this rover around? And remember, we have this big separation between Earth and Mars so that the speed of light is a real factor. So what we don't do is we don't joystick it. I know there's some kids here. It's not like we're doing an Xbox game. Because the problem is, you know, if the rover's driving along the podium here and it's about to go off the cliff, by the time you see that, it's happened 7 minutes ago. So, you know, we don't want to have that kind of terror either. And so basically what happens is that we basically drive it by sending emails back and forth to Mars. That's basically what it amounts to. And so just after sunrise on Mars, we send a command via the Deep Space Network on Earth, a direct to Mars command to the rover to tell it to basically wake up and here's what it should do. And then just before sunset on Mars, it sends us a message stream back that tells us what it did do on Mars. And then all of the big high data volume data products, they get sent back via this UHF radio that communicates to 2 different satellites. And all our big data then gets sent back because these orbiters are built with much more powerful transmitters. And so they can handle that data volume. And that's basically how it works. And so we're constrained basically to getting this critical, what we call critical data, twice a day. We send it and then we receive it. Now, in the Mars yard up at JPL, we can sort of joystick it around. In fact, these guys, these rover drivers, Matt Heverly here, they have all the codes on their iPhone, and so they drive it around with their iPhones. And basically what we're doing is we're practicing and testing out the rover. Remember this whole business of testing. So here's a simulation that we did up in the Mars yard for our first drive. And this is not something we're going to do every time we drive on Mars, but if we ever have any concern, we always test it out first. So we take that camera and we take a picture of our environment in 360, and then we basically project the images as if you were hovering above the rover and looking down on the ground, maybe like Skycrane did. So there's no data where the rover is because it can't take pictures of itself. So it's basically scanning out in 360 degrees, and in this direction, which we wanted to drive, it's great data. You can see all of the grayscale pixels turned on here because it sees the terrain everywhere. Over here, there were some rocks sticking up, so where you see the tan color, that's a shadow, is basically what's happening. So we wanted to drive in this direction, but this was also the safe direction to drive in. Nevertheless, this was the drive that we wanted to plan using the software that we used to command the rover. And then on Earth, we build the same thing in the test bed and practice that drive before we actually execute it on Mars. So now I'm going to show you a movie of Curiosity's first drive. That was the one that we planned in the test bed and using the software on board the rover. Basically now it will be commanded to drive forward 3 meters. You'll see the cameras swiveling around here and taking pictures all the time. We want to see the wheel tread. We want to see the terrain that we're driving over. We want to see if we're kicking stones up and trapping them. And we want to make sure more than anything that the wheels turned the way they were supposed to turn when they were supposed to turn that way. So then we go forward, we do this arc turn in place and then back up 1 meter, and now you'll see the camera head swivel around here again and basically take pictures back at the drive. And so then what we're going to do is compare that, what we programmed it to do, with the actual. And so this is the actual. Here are the pictures that it took after it did this drive away from the landing site. And this is where Sky Crane dropped it down. And the first time in human history, you don't actually see a lander here. There's no LEM, there's no platform that the rover rolled off of. Just got dropped out of the sky here. And so you see these tracks basically going back to zero with the scour marks from the thrusters on Sky Crane on both sides, and then Mount Sharp back here in the background. So now we were off on our science mission, and now we're going to go back up to the orbiters and look down at the ground. Here's Curiosity. It's painted white, so it's very bright on this picture. This is a false color image, so these aren't the real colors of the planet. But it's light because it's so reflective. And then you can see the scour marks where the thrusters really blew the soil away. And then this area here is an area where the dust was kind of wafted away, enough to change the color balance that you can see from orbit. But you don't have to be a geologist to see that there's basically three fundamentally different terrains here. There's this terrain, which sort of has this hummocky look. Then there's a terrain over here with all these craters that looks like the surface of the moon. And then there's a terrain over here that is very light-toned, and it doesn't seem to have many craters in it. So they're very distinctive. This is the terrain that from orbit gave us the glowing red response that we saw in that thermal map. This is the stuff that we really wanted to go check out, but the cool thing was, if we went over here to check it out, we could also go to the place where all three of the terrains came together, and we sort of get a threefer by going in that direction. So we felt that it was very much worth the risk to drive in the opposite direction, a relatively short distance to try to get that. Now on the way, we already began to find really cool stuff. And so what we've got here is something that geologists call a pebble conglomerate. That's code for a solidified gravel. And what you can see here are pebbles of rounded rock. This is on Earth. This rock is only 10 million years old, which is really, really young, even for the Earth. And what you've got here is evidence of flowing water. And this is really intuitive. You don't need a PhD in geology to get this. You have pebbles in a stream, they flow in the water, they bounce and hit each other, and they get rounded off, and they make these rounded objects. This is the same thing on Mars. The only difference is that this rock, as best as we can tell, is 3.5 billion years old. So the rover basically landed on an ancient stream bed. That's what we were able to conclude about a month into the mission there. So that's cool. And what we wanted to do then, we got a really strong indicator that what we saw from orbit was really working out on the ground. And now what we have to do is go with the flow. We want to keep driving that rover downhill in the direction that the water would have been going. So, this is the same thing that you would do on Earth. You have some mountains. This is down in the Andes, which is really dry. The mountains go up. Weathering happens, it rains, the water flows, it breaks up bits of rock, transports them in these channels, they bang against each other, and this angular one will eventually become rounder like this one. But if you go far enough, you get the really fine-grained equivalent of it, where the flow velocities start to slow down and they can no longer transport these really coarse ones. You're looking for the fine stuff, because that's where on Earth we know to go to get the kind of materials that we're looking for to demonstrate these habitable environments. So that's what we wanted to do, was try to find a way to get downstream, so to speak. So that's the way we did it, was to recognize that this direction was also downhill. It was also going into relatively older rocks, which was important. So we go along, and the geologists give them all different names, and as we go along, we stop, and every place you see a little yellow diamond is where the rover stopped and then planned the next drive. Now, one thing that we had to do before we started to drill was to clean out our sampling system, and for that, we needed to get a material that was very sandy. And I won't go into the details in the interest of time, but we needed sand. So we found it here at this location called Rock Nest, and then we basically took about a month to analyze this sand. So here's what we do. We reach that turd out, and we reach down, we open up the scoop, and then we just dig right into it. And then the scoop comes up, it hovers in place, and what we've got is a heaping teaspoon, but we don't want the heap. So what we do is we command the rover to vibrate the tablespoon, and all the stuff that we don't want then goes sloughing off the top. Here's the heap, and now you're left with a level tablespoon. And that's what we were after. Then you close this clamshell up, and then you start to shake it around, And that is the way that you clean out the sampling system. If there's any grime in there, you want to get it off onto these sand grains and then dump them away. So here's a picture we took when we were almost done. We had now scooped 4 times. This is the first scoop. Here's the second scoop. Here's where we leveled them off. And then we took this 3rd scoop and the 4th scoop, and we basically dumped that into now the rover, into the instruments for the first time. And we analyzed it. And in the interest of time, I won't go into that, but we got already really interesting results from that. But we wanted to keep going, and we wanted to keep going towards this rock that was down here that we saw from orbit. So basically, this green dashed line is where from orbit you look down and you cross over the one terrain that doesn't retain its heat so easily into the terrain that does retain its heat more capably. And when you cross this green dashed line, that's when you, from orbit, you predict to see a response on the ground. So notice that we basically did that on the drive between Sol is a Martian day, Sol 120 and Sol 121. We crossed that boundary. Here's some data up here. It's the only data I'm going to show you from the weather station in this presentation. But basically, you can see the scale over here. Here's minus 100 degrees centigrade. Here's 0. Here's plus 20. And then these are the sols. And so basically, after 100 days of operation, we're going up and down. And basically, the nighttime low is always about the same. The daytime high is always about the same. But we cross that boundary as we go from Sol 120. And sure enough, we see this property of thermal inertia kick in. The nighttime lows don't get quite as low, and the daytime highs don't get quite as high. Now, we still don't know what this means, but when we crossed it and we got this response, we knew we were getting closer and closer to the material we wanted to go to. Okay, so this is what it looks like. And so you cross that boundary, you've looked at it for years from orbit, wondering what is this boundary going to look like when you get on the ground, and what you see is something that looks like Moab, Utah. It'd be a great place to go mountain biking. It's solid rock, and that might have something to do with its ability to retain heat better than this kind of loose, gravelly soil here, but we haven't done the work to demonstrate that, so I'm not going to say much more about that. But the point is that all these rocks down here, this is the good stuff. So what we decided to do is command Curiosity to drive around this ledge over here, turn the corner, and then come down, and now she's over here just out of the way is where the drilling all occurred. And when we got there, it was the world changed. When we crossed that boundary, the thermal inertia, everything started to look different. And what we found was a rock that was basically shot through with veins. And if you've ever been on a trip somewhere, a tourist trip to go to an old mining district, that's just what miners are looking for. They're looking for rocks that have been broken up and are full of veins, because that's where the fluids move through. And when we saw this, we realized there wasn't just water flowing across the surface, there was water coming up through all these rocks and through these fracture networks. And here's an analog from Earth with a penknife for scale, exactly at the same scale that if the penknife was here on Mars, that would be about the same size. And you see these fractures on Earth, and we know from studies for at least 150 years now that the minerals that form in these fractures were created by water percolating through this rock. So we know that this is really working out well now, but we still don't know what the composition is. We used our laser, and our laser told us that this was a calcium sulfate mineral and probably hydrated, so that was very encouraging. So then we decided to drill, and we looked around, and the geologists were all on the team. We're trying to pick targets that looked very attractive, and they're signing their usual names. And then the engineers got involved. We found the spot where we wanted to drill, and they just decided to call it drill. That sort of illustrates one of the basic differences. Why waste time naming things? But this is basically where we decided to go for it. And now, I'll show you what basically happened when we drill, but I want to put this in a little bit of a historical context. What do you get for a decade of science iteration on the ground and in orbit in terms of trying to pick a place to land this mobile laboratory? Here's back a decade ago with Opportunity landing at Meridiani. And at that time, we couldn't drill, but what we could do is sort of rasp away. It'd be like taking a piece of sandpaper and rubbing down a block of wood. So we get down about 1 millimeter, and when we do that, we create dust. And the interesting thing about that dust is that dust is red, just like the planet's red. And the reason the planet's red is because the dust is red. And the reason the dust is red is because there's iron in it that's been highly oxidized. And this was, after Viking, people looked at this and said, Mars is just not the greatest surface environment for a whole bunch of reasons, one of which is that it's very oxidizing. having looked at all this iron oxide that was there. So the red color basically meant that the rock, this very ancient rock, was also probably formed in a very oxidizing environment. What we also learned as we did more chemistry on this rock was that it was formed in an environment that was extremely salty. Maybe so salty that microorganisms couldn't live, much the same way that if you put honey on your shelf and you wonder why it doesn't spoil, the reason why is that the activity of water is so low in that honey that any microbe that falls into that jar of honey is going to get the water sucked right out of it. So that's not a habitable environment, even though there's water there. Okay, so conceptually, this is important to make this point, that this is what we do when we go beyond looking for water on Mars. We're trying to characterize the chemistry of the environment. This wasn't good. The more we looked at this, super salty, really oxidizing, and not only that, but we don't see any diversity of minerals here other than minerals that have one, what chemists call valence state, and the iron is all extremely oxidized, as oxidized as you can get. When we drilled into our spot there at Gale Crater, we saw a different kind of Mars. We saw gray Mars. And basically, this came as a result of all the mapping that led us to this area. And when we got down there, we still didn't know if we were going to get surprised, because here's red Mars. This is what the surface looks like. But you scratch beneath the surface here, and you get the gray color. And that's important, because if nothing else, it's a little bit like looking at maps of just seeing water flowing. You don't want to get too sophisticated and try to second guess. But on Earth, here are ancient rocks that come from the same place. They're about 300 million years old. This one is red, and this one is gray. And if you are doing geobiology and looking for signs of life on the early Earth, this is where you want to be. Not because the life is preserved there, but because the environment allows life, if it was ever present, to be preserved there. So this is one of the big questions that we're working through right now on the mission is, how can we go about looking for preserved organic carbon? And this gray is the first hint that things are beginning to line up better than they have been in the past. So we drilled it, and then we process it, and we send it through the scoop. And this is another one of our iconic images from the mission. It shows that the technology works. That's extremely important. Hats off to the engineers. But you have this gray-green color material here, and there, what you see plastered onto the side is what we call cross-contamination. This is the dust and silt that's left over from when we stopped to scoop up that soil. So we can't get rid of that. Once it's in the scoop, we have to pass forward to each sample a little bit from the previous sample. So here again, you've got red Mars in the soil and gray Mars in the rock. Okay, so then came time to take that material and pass it through this X-ray diffraction unit. And I'll just explain real quickly how that works. So we have a source of X-rays. It basically makes a beam through this, what we call a collimator. It's a little pinhole. And so you basically get this very narrow dispersion of the X-ray beam. And the differences between labs on Earth and this lab is that the miniaturization involved taking the sample and allowing the sample to move around while the X-ray stores stayed in place. And so basically, we have a little piezoelectric device that makes the sample vibrate, and it kind of churns around, and then the X-rays bombard it. They're scattered, and then we basically have this CCD back here that the pixels basically turn on when they get interacted with. And again, I'll just leave it at that, but it's amazing how well this works. And here's what you get from it. This is the diffraction pattern from this sand deposit, as it's called, sand shadow. And this was an interesting place, but it wasn't really exciting for a story about water, much like we expected to see for sand on Mars, which we know to be a very dry place. Here's the sample from where we drilled the rock, and you get all these different rings, and they're all telling you about different kinds of minerals that are there. But I just wanted to highlight one of them here, which is right down here at the narrowest angles. We have a mineral that we call phyllosilicate. Now, you will know that more simply as something called clay. A clay mineral. The important thing about clay minerals is that they have water in their structure. So this is a rock that's billions of years old, but it's on a dry planet, but it's still retaining its water. That's really cool. So what that does is it means that we're getting closer to understanding this environment, which we know from the chemistry is low in salt, and now we know from the mineralogy that these clays only form in more neutral pH environments. That rock that we explored with Opportunity 10 years ago was one of the most acidic places you could ever imagine, probably pH 1, something like that. It's not completely inhabitable based on pH. You have to bring the salt argument as well, but what we've got in this sample here is basically low salt, low pH. Okay, so now we can go a step further and work on it with our most complicated instrument, the SAM instrument. And what I want to do here is sort of dazzle you with a long list of things that you should take away as meaning this thing's incredibly complicated, and that's why it costs $90 million to build. Here's a diagram that is supposed to be dizzying. And basically, this is just the plumbing system. This isn't even the electronics, but it basically shows the number of valves that have to open and close in order for the science team that uses this instrument to basically operate it. If I simplify that for the sake of showing you what we've done, here's a much simpler mapping of it. What we do is we take the sample, I need to change this actually, it's either the scooped soil or the drilled rock, either one. It goes into the sample manipulation system, which is over here, and we basically have these cups that are made out of quartz. And we dump the dirt into the quartz cup, and then the quartz cup comes out of the carousel, it moves into an oven, and we basically heat it up. And then as we heat it up, we can choose to route it into these 3 different instruments here, depending on exactly what we want to do with it. So basically what's going on is that we put this thing in the oven, and the simplest way to explain it, it's like baking a cake. You walk into the room, you don't know there's a cake in the oven, but you know there's something in there because you can smell it. So what we are doing is heating this rock sample up to about 1,000 degrees centigrade, 800 to 1,000 degrees centigrade, and all the volatiles are coming off. So when you bake that cake, what's happening is that the water's coming out of the cake at about 60 degrees centigrade. The carbon dioxide's coming out of the cake because you put baking powder in it. And it's also bringing a little organics around, which is what you're smelling there. So this is effectively what we're trying to do. We generate these gases, and then we route them into these spectrometers to basically study their composition. And then if we want to, after heating it up, we then put it over a cold trap, which is freezing, and basically if there's any hydrocarbons in there, they'll condense out. And then we heat that up again, and we can pass into this instrument and look for organics. It takes a lot of time to do, but the fact is it's all working pretty well. I'll just show you a little bit of data to show you what comes out of one of the instruments. And basically what's happening is here's your temperature scale down here, and this is the signal that the instrument sees as it works, this quadrupole mass spectrometer. And so we're heating the sample up, and now the vapors are coming off. And just like the cake, one of the things that comes off real early is water. So this is a signal of water coming off here. And then shortly after that, what's happening is that we get carbon dioxide coming off, and we also get oxygen coming off. And each one of these gases that we sniff with the rover is basically peaking, and then it dies away. And what's really important about this are these guys up here. These are 2 different forms of sulfur, and I won't go into the details other than to say that one of them is hydrogen sulfide, one of them is sulfate, and those are 2 different oxidation states of sulfur. And that's really important if you're a microbe, because that means that you're able to basically do redox chemistry the way that some types of microorganisms like to do. I won't say anything more about this other than to say that this is the kind of data that allows us to reconstruct what it is that microorganisms could have been feeding on if they had ever been there. So what about the feeding? What we're not doing here is trying to reconstruct environments for higher life forms. We're asking if the simplest organisms that we know on Earth, these bacteria, prokaryotic microorganisms, they basically live by feeding on rocks. That's where they get their energy from. It's like a chemical energy. They don't need sunlight and stuff like that. We're used to thinking about these organisms over the past 20 years as living in extreme environments. They live in ordinary environments, but when you think about Mars, historically you think of it an extreme environment, something really harsh. So it was exciting when people, you can walk on this boardwalk here at Grand Prismatic Spring at Yellowstone, you got boiling water. 20 years ago, people didn't think that microorganisms could live in that boiling water, and actually there are some that live around 110 degrees centigrade and lower. And as the water basically spreads out from this vent, it's kind of boiling up here, it spreads out, the temperature drops, and then the different colors that you see here are different pigments in these microorganisms that live here. And they do interact with light, but the ones we're talking about derive their energy just from simple chemical reactions. That's one kind of extreme environment. Here's another type. This is the extreme environment that we reconstructed 10 years ago based on the data that we got from the Opportunity rover. Get on the plane, go over to Spain. You see this place called Rio Tinto. It's one of the oldest mines on Earth. It was mined already back in the times of the Romans. And they produce sulfide minerals from there. And those minerals basically weather in the Earth's atmosphere and produce sulfuric acid. And the pH just drops right down. The pH gets so low that iron actually will dissolve and be present in the water in the +3 state. That's really unusual because normally what happens is iron combines with oxygen and it just dumps right out. So the Rio Tinto, the river is red here because the pH is so unbelievably low, yet there's microbes living all over the place here. This is an extreme environment. They can handle the pH, but if you hit them with the salinity as well, they're not going to be able to make it. But these are the reference analogs that we had been studying on Earth until this mission. And now we've got, basically, we can reconstruct with the chemical laboratory that we had an environment that was not like honey. It was actually a very dilute solution. And we see in the minerals and the chemistry that was there, basically batteries. They're like little chemical batteries that are in these rocks that the microorganisms could take advantage of. And where all this leads us is to not an extreme environment, but kind of an ordinary environment. One on Earth, you just go to Western Australia, you can find these things here in the US as well. It rains, the water percolates down through the rock, and it comes up in these temporary lakes that fill up from time to time. But if you dig down in those things and you get your shovel out and you scoop it out and let the water accumulate in there, this is the kind of water that, I don't want to make too much of a big deal out of it, but I told the media, they said, can you explain this in simple terms? I said, well, compared to the kinds of water we've discovered in the past, this is the kind of water that if you had been out in the desert and needed a glass of, you'd probably be pretty happy to get it. You wouldn't actually curl up and die, unlike that water that you would see there in Rio Tinto. Okay. So this leads me to the end. You can see what we've learned there from the science. And right after we landed, Time magazine covered this mission and put it on the cover. And it asked the question about what you could learn from a robot 154 million miles away. We are now about 230 million miles away. But this was the answer. And basically, it's really about the extraordinary things that go on here at Caltech and JPL. And I think for me, to be involved in this mission, it was really to be involved with these engineers and learn things that I had never really appreciated before. But I think this is what the people are seeing here, that this kind of a mission is something that breaks that gridlock in Washington and that everybody in this country can really feel proud about for having contributed to and work on. It is amazing engineering, and I think now JPL has sort of a brand name recognition opportunity. When you hear the term system engineering, that's what it takes to make a mission like this happen. So thanks for listening. Okay.